Imagine standing by the ocean. You see waves rolling toward the shore. Some are tall and powerful, others are small and gentle. The height of these waves is what we call their amplitude. A wave with a large amplitude carries a lot of energy, like a towering tsunami. A wave with a small amplitude is much calmer, like a gentle ripple in a pond. Amplitude tells us about the intensity or strength of a wave. It is a fundamental property that we can see and measure quite easily in the world around us, from the loudness of a sound to the brightness of a light. It is one of the two key pieces of information that define any wave. Now look closer at those ocean waves. You might notice that they have a rhythm. The peaks and troughs follow each other in a predictable pattern. This rhythm is related to the wave's phase. Phase tells us where a wave is in its cycle at a particular moment. Is it at its highest point, its lowest point, or somewhere in between? If two waves have their peaks and troughs aligned perfectly, we say they are in phase. Their combined effect is a much larger wave. If the peak of one wave aligns with the trough of another, they are out of phase. They can cancel each other out, resulting in calm water. Phase governs how waves interact, interfere, and combine. These two properties, amplitude and phase, are not just for ocean waves. They describe all waves. Sound waves have an amplitude that determines their volume and a phase that affects how they combine in a concert hall. Light waves have an amplitude that determines their brightness and a phase that is crucial for creating phenomena like holograms. For centuries, classical physics provided us with the mathematical tools to understand and predict the behavior of these waves. We learned to measure their height and track their rhythm, building technologies like radio, radar, and lasers based on this classical understanding of wave mechanics. But there is a hidden world, a realm far smaller than ocean waves or even light waves, where the rules are different. This is the quantum realm. Here, particles like electrons and photons also behave like waves. They too have an amplitude and a phase. However, these quantum waves are waves of probability. Their amplitude tells us the likelihood of finding a particle in a certain location. Their phase governs how these probabilities interfere and evolve. To truly understand the universe at its most fundamental level, we must look beyond our classical intuition and embrace the strange and powerful language of quantum mechanics. Classical physics gives us a solid intuitive picture of the world. It sees waves as continuous flowing entities. An ocean wave can have any height and its energy can be any value. This view works perfectly for the large-scale world we experience every day. However, when we zoom in to the atomic and subatomic scales, this smooth, continuous picture begins to break down. Classical physics struggles to explain the behavior of light and matter in this tiny realm. It was here at the turn of the 20th century that a revolution began. Scientists discovered that energy was not continuous but came in discrete packets, or quanta. This was the birth of quantum mechanics. Quantum mechanics offers a completely new and more powerful lens for analyzing wave properties. It tells us that particles, which we once thought of as tiny solid balls, also have a wave-like nature. An electron, for instance, is not just a point particle orbiting an atom's nucleus. It is also a wave of probability spread out around the nucleus. The amplitude of this electron wave at any given point tells us the chance of finding the electron there. This concept, known as wave-particle duality, is a cornerstone of quantum theory. It means that the tools we use for waves, like phase and amplitude, are essential for understanding the fundamental building blocks of matter. The superiority of the quantum approach lies in its ability to handle this strangeness. While a classical wave's amplitude is just a measure of its physical strength, a quantum wave's amplitude is connected to probability. Specifically, the square of the amplitude gives the probability. This probabilistic nature is a radical departure from the deterministic world of classical physics, where if you know the starting conditions, you can predict the future with certainty. In the quantum world, we can only predict the likelihood of different outcomes. The phase of a quantum wave becomes even more critical, as it dictates how these different probabilities interfere with each other, leading to uniquely quantum phenomena. This new perspective allows us to probe nature with unprecedented precision. Quantum mechanics provides the mathematical framework to describe not just one particle wave, but systems of many interacting ones. It explains why electrons in an atom can only have certain energy levels, because their waves must fit perfectly around the nucleus, much like a guitar string can only produce certain notes. Classical physics could not explain this. By embracing the wave nature of matter and the probabilistic core of reality, quantum mechanics unlocks a deeper understanding of phase and amplitude, giving us the tools to not only describe the universe, but to manipulate it in ways previously unimaginable. In our everyday world, we describe the state of an object with familiar properties, like its position, speed, and temperature. A baseball's state could be moving at 90 miles per hour towards home plate. This is a classical state. It's definite and singular. Quantum mechanics, however, requires a new concept to describe the conditions of a particle, the quantum state. The quantum state is a complete mathematical description of a quantum system. It doesn't just tell you where a particle is or how fast it's going. Instead, it contains all the information about all the possibilities. It is a catalog of potential realities for that particle. Think of an electron. Before we measure it, its quantum state doesn't give it a single fixed position. Instead, it describes a wave of probability, often called a wave function. This wave function assigns a specific amplitude and phase to every possible location the electron could be. Where the amplitude is high, the probability of finding the electron is high. Where the amplitude is zero, there's no chance of finding it. The quantum state is therefore not a snapshot of what is, but a comprehensive map of what could be. It holds the potential for the electron to be here, there, or many places at once, all encoded within its complex wave structure. This idea is profoundly different from classical intuition. A classical object has one reality. A quantum object, when unobserved, exists in a state of many potential realities simultaneously. The quantum state is the recipe that holds all these ingredients together. When we perform a measurement, for example, when we use a detector to find the electron's position, this delicate state of possibilities collapses. The wave function instantly changes, and the particle is forced to choose one definite outcome from all the possibilities. The probability of any specific outcome is determined by the amplitude of the wave function at that point just before the measurement. Understanding the quantum state is the first step to unlocking the power of quantum mechanics. It is the language we use to speak about the subatomic world. By learning to prepare, control, and manipulate these quantum states, we can harness their unique properties. We can use the phase and amplitude of these probability waves to perform calculations, send information, and measure the world with astonishing accuracy. The quantum state is the fundamental unit of quantum information, the qubit in a quantum computer, and the key to understanding everything from the stability of atoms to the bizarre connection of entanglement. It is the playbook for the quantum world. One of the most mind-bending concepts that arises directly from the quantum state is superposition. In simple terms, superposition is the ability of a quantum system to be in multiple states at the same time. This isn't like a spinning coin, which is rapidly alternating between heads and tails. It is truly being in a combination of both heads and tails simultaneously. A single particle, like an electron, can be in a superposition of different locations. It can literally be in several places at once. It can also be in a superposition of different energy levels or spin states. This is not a metaphor, it is the reality described by the mathematics of quantum mechanics. To visualize this, let's return to our wave function. A wave can have multiple peaks. If the wave function of an electron has two distinct peaks, it means the electron is in a superposition of being at the location of the first peak and the location of the second peak. It is not that the electron is at one of the two spots and we just don't know which one. The electron state is genuinely a combination of both possibilities. The amplitude of the wave at each peak tells us the probability of finding the electron at that specific location if we were to make a measurement. The relative phase between these two parts of the wave determines how they will interfere with each other. The most famous demonstration of superposition is the double-slit experiment. When we fire individual particles like photons or electrons at a barrier with two narrow slits, something remarkable happens. Each particle seems to pass through both slits at the same time. It exists in a superposition of going through the left slit and going through the right slit. The two paths represented by two parts of the particle's wave function then interfere with each other. This interference, governed by the phase difference between the two paths, creates a distinctive pattern of bright and dark bands on a detector screen behind the slits, a pattern that could only be formed by a wave. Superposition is not just a philosophical curiosity, it is the engine behind the power of quantum computing. A classical computer bit can be either 0 or 1. A quantum bit or qubit can be in a superposition of both 0 and 1 at the same time. This allows a quantum computer to explore a vast number of possibilities simultaneously. A computer with just a few hundred qubits could perform calculations that would take the most powerful classical supercomputers billions of years to complete. Superposition transforms a single particle from a simple switch into a powerful parallel processor, all thanks to the strange logic of quantum waves. Section 5. Entanglement, a spooky connection across space. If superposition challenges our intuition, then entanglement shatters it completely. Albert Einstein famously called it spooky action at a distance. Entanglement is a unique quantum phenomenon where two or more particles become linked in such a way that their fates are intertwined, no matter how far apart they are. their individual quantum states can no longer be described independently. Instead, they share a single, unified quantum state. Measuring a property of one particle, such as its spin, instantly influences the corresponding property of the other particle, even if it's on the other side of the galaxy. Imagine you have a pair of entangled electrons. Let's say they are entangled in their spin, a quantum property that can be up or down. The entangled state might be set up so that if one electron is measured to have spin up, the other must instantly be found to have spin down, and vice versa. Before the measurement, neither electron has a definite spin. They are in a superposition of possibilities. But the moment you measure the first electron and find it has spin up, you know with absolute certainty that the second electron, wherever it is, now has spin down. This connection is instantaneous, seemingly faster than the speed of light. This doesn't mean information is traveling faster than light. You cannot use entanglement to send a message. The outcome of the measurement on the first particle is random. You can't force it to be spin up to send a 1 or spin down to send a 0, but the correlation between the measurement outcomes is perfect and mysterious. This deep connection is encoded in the shared wave function of the entangled pair. The phase relationships within this complex multiparticle wave function ensure that the states remain perfectly correlated. The system behaves as a single, coherent whole, even when its parts are separated by vast distances. Entanglement is a vital resource for quantum technologies. It is the key to building secure quantum communication networks. In a process called quantum cryptography, entangled particles can be used to create unbreakable encryption keys. If an eavesdropper tries to intercept and measure one of the particles, the entanglement is disturbed and the disruption is immediately detectable. Entanglement is also crucial for quantum computing, as it allows qubits to be linked together to perform complex calculations. This spooky connection, once a source of philosophical debate, is now a practical tool for building the next generation of technology. Section 6. Quantum tools for a deeper look. The power of interferometry. To harness the delicate properties of quantum waves, we need incredibly sensitive tools. One of the most powerful techniques for measuring phase is interferometry. A classical interferometer works by splitting a beam of light, sending the two beams along different paths, and then recombining them. If the paths have different lengths, the waves will be shifted in phase relative to each other when they meet again. This phase difference creates an interference pattern of light and dark fringes. By analyzing this pattern, scientists can measure tiny differences in distance with extreme precision. This principle is used in everything from telescopes to gravitational wave detectors like LIGO. Quantum interferometry takes this concept to a whole new level by using the wave nature of individual particles. Instead of a bright beam of light, we can send a single photon or atom through an interferometer. Thanks to superposition, that single particle travels along both paths simultaneously. Its own wave function is split, and the two parts journey through the arms of the interferometer before recombining. The particle then interferes with itself. The probability of where the particle will be detected depends on the phase difference it accumulated between the two paths. This allows for measurements of forces and fields with a sensitivity that classical methods cannot approach. This technique is incredibly powerful for phase and amplitude extraction. For example, if one path of a quantum interferometer is exposed to a weak magnetic field, it will slightly alter the phase of the particle's wave function traveling along that path. When the wave recombines, this tiny phase shift will change the final interference pattern, revealing the presence and strength of the magnetic field. Because quantum states are so fragile, they are extremely sensitive to their environment. This makes quantum interferometers ideal for creating ultra-precise sensors for gravity, rotation, acceleration, and magnetic fields, far surpassing the capabilities of their classical counterparts. The precision of quantum interferometry is foundational to many areas of modern science. In quantum optics, it allows us to study the fundamental nature of light and its interaction with matter. In metrology, the science of measurement, it is used to define standards for time and length with unprecedented accuracy. Atomic interferometers, which use atoms instead of light, are being developed for navigation systems that do not rely on GPS and for detecting subtle variations in Earth's gravitational field to find underground resources. By leveraging superposition and self-interference, quantum interferometry turns the strangeness of the quantum world into a practical tool for discovery. The abstract principles of quantum mechanics are no longer confined to textbooks and laboratories. They are actively being translated into revolutionary technologies that are beginning to shape our world. The precise control over quantum phase and amplitude is the driving force behind these advancements. One of the most prominent fields is quantum computing. By using qubits that exist in a superposition of states and linking them through entanglement, quantum computers promise to solve problems that are currently intractable for even the most powerful supercomputers, from designing new drugs and materials to breaking complex codes. In the field of quantum sensing, the extreme sensitivity of quantum states to their environment is being exploited to create next-generation detectors. Magnetoencephalography, or MEG scanners that use quantum sensors, can map brain activity with much higher resolution and without the need for cryogenic cooling required by conventional machines. Quantum gravimeters can detect minute changes in gravity, which could be used to monitor volcanoes, find underground water reserves, or discover hidden archaeological structures. These sensors work by precisely measuring the phase shifts in quantum systems, like clouds of ultra-cold atoms, as they are affected by external forces. Quantum communication is another area undergoing rapid development. Standard communication is vulnerable to eavesdropping. Quantum cryptography, however, offers a solution for perfectly secure communication. It often uses entangled photons to distribute a secret key between two parties. According to the laws of quantum mechanics, any attempt by a third party to intercept and measure the photons will disturb their quantum state. This disturbance is immediately detectable, alerting the legitimate users that their communication has been compromised. This guarantees the security of the communication channel, a feature impossible to achieve with classical methods alone. Furthermore, quantum metrology is redefining the limits of measurement precision. Atomic clocks, the most accurate timekeeping devices ever built, are based on the incredibly stable and predictable oscillations of electrons in atoms, a purely quantum phenomenon. These clocks are essential for GPS, financial networks, and scientific experiments. Researchers are now developing so-called nuclear clocks that promise even greater stability. By harnessing the phase and amplitude of quantum states, We're not just improving existing technologies. We are creating entirely new capabilities that will push the boundaries of science, medicine, and information technology. For any measurement, there is always some level of uncertainty or noise. Classical physics recognizes this, but it also imposes fundamental limits on how precise a measurement can be. One of the most important classical limitations is the shot noise limit, also known as the standard quantum limit. This limit arises from the particle-like nature of light and matter. When you try to measure something with a beam of light, for instance, you are actually measuring it with a stream of individual photons. Since the arrival of these photons is random, there is an inherent statistical fluctuation in the signal, much like the patter of raindrops on a roof. This shot noise limit dictates that the precision of a measurement improves with the square root of the number of particles used. To make your measurement twice as precise, you need to use 4 times as many photons. To make it 10 times more precise, you need 100 times as many. This becomes very inefficient and costly, especially when dealing with delicate samples that can be damaged by too much light or when you simply run out of power. For many sensitive applications, such as detecting gravitational waves or imaging fragile biological cells, the shot noise limit represents a significant barrier that classical techniques cannot overcome. This is where quantum mechanics offers a remarkable advantage. By using clever quantum states such as entangled or squeezed states of light, it is possible to bypass the shot noise limit. Squeezed light is a special quantum state where the uncertainty is manipulated. The noise is squeezed out of one property, like amplitude, and pushed into another, like phase, where it doesn't affect the measurement as much. This allows for a measurement that is more precise than what would be allowed by the shot noise limit. For the same number of photons, it's like quieting the statistical hiss to hear a fainter signal. This quantum advantage is not just theoretical. It is already being implemented in advanced experiments. The LIGO and Virgo gravitational wave observatories now use squeezed light to increase their sensitivity, allowing them to detect fainter and more distant cosmic events like the mergers of black holes and neutron stars. By preparing photons in specific highly correlated quantum states, we can essentially make them work together more efficiently than independent classical particles ever could. This ability to manipulate quantum noise and correlations allows us to push beyond classical barriers and peer deeper into the universe. While quantum mechanics allows us to surpass the classical shot noise limit, it does not offer infinite precision. There is a more fundamental boundary set by the laws of physics themselves, known as the Heisenberg uncertainty principle. This principle states that there is a fundamental trade-off in how precisely we can know certain pairs of properties, like a particle's position and its momentum. The more accurately you measure one, the less accurately you can know the other. This principle gives rise to the ultimate boundary in measurement precision, the Heisenberg limit. The Heisenberg limit represents the absolute best precision that quantum mechanics allows for a given number of particles. Unlike the shot noise limit, where precision improves with the square root of the number of particles, the Heisenberg limit states that precision can, in principle, improve directly with the number of particles. This means that to make a measurement twice as precise, you only need to use twice as many particles, not 4 times as many. This is a huge improvement in efficiency and represents a quadratic leap in sensing capability compared to classical approaches. Reaching this limit is the ultimate goal of quantum metrology. Achieving the Heisenberg limit requires exploiting the full power of quantum mechanics, particularly entanglement. By preparing all particles in a highly entangled state, often called a noon state, they can be made to act as a single cohesive quantum object. This collective entity has a wave function that oscillates much faster than that of a single particle. A faster oscillation means that any small disturbance will cause a much larger, more easily detectable phase shift. This is how entanglement allows the particles to pool their measurement resources in the most efficient way possible, pushing precision all the way to the fundamental Heisenberg limit. While experimentally challenging, scientists are making significant progress toward Heisenberg limited measurements. They have demonstrated the principle with small numbers of photons and atoms in laboratory settings. The pursuit of this ultimate limit is driving innovation in the creation and control of complex, entangled states. Reaching this frontier will enable technologies we can only dream of today, such as clocks so precise they could detect the warping of space-time across a tabletop, or sensors that can image the inner workings of a single protein in real time. The Heisenberg limit is not a barrier to be broken, but a summit to be reached, representing the pinnacle of what is physically possible in the art of measurement. Our journey from the familiar waves of the ocean to the ghostly probability waves of quantum mechanics reveals a profound shift in our understanding of reality. The simple concepts of phase and amplitude, once used to describe light and sound, have become the keys to unlocking the deepest secrets of the universe. Classical physics gave us a solid foundation, but it was a foundation with limits. Quantum mechanics provides us with the tools to build far beyond those limits, turning the strange and counterintuitive features of the subatomic world into powerful assets for technological and scientific progress. The ability to precisely read and write the information encoded in the phase and amplitude of quantum states is the cornerstone of this new technological revolution. Superposition allows for immense computational parallelism. Entanglement creates unbreakable connections that defy distance. Quantum interferometry provides a lens to see the world with a clarity that was previously unimaginable. These are not just incremental improvements, they are paradigm shifts. They represent a fundamental change in how we interact with the world, moving from passive observation to active manipulation of the very fabric of reality. The path forward is filled with both challenges and immense promise. Building stable, large-scale quantum computers and deploying global quantum communication networks will require overcoming significant engineering and scientific hurdles. We must learn to protect fragile quantum states from the noise of the environment, a phenomenon known as decoherence. Yet, with each passing year, researchers are pushing the boundaries of what is possible, creating more robust qubits, entangling more particles, and building sensors that approach the fundamental limits of precision set by nature itself. As we stand here in 2025, we are witnessing the dawn of a new quantum age. The secrets of wave phase and amplitude, once hidden in the quantum realm, are now being brought into the light. From medicine and material science to computing and cosmology, the applications of this knowledge will be transformative. By continuing to explore this fascinating domain, We are not just unlocking the secrets of quantum waves, we are charting a course toward a future where the deepest laws of the universe are harnessed to solve some of humanity's greatest challenges and to propel us into a new era of discovery.